I'm here with Ben Station from Stationcraft Inc. So Ben, we've now built a very airtight home. What is the mechanical contractor's role in ensuring that home is efficient and comfortable for the end user?
Yeah, so the mechanical contractor is going to come in and they're going to install our mechanical systems to make sure that the home stays comfortable and healthy. We have three main mechanical systems that are going to exist within the home. It's the heating and cooling system, the domestic hot water system, and the ventilation system. All of those work together to influence how the energy is consumed within the home, and we want to make sure that our mechanical contractor is selecting very high quality and efficient equipment that's suited to the build itself. So we need to be making sure that we're approaching this from a design perspective right at the beginning of the build and involving our mechanical contractor so that they know what they're doing right from the very beginning of the build, and we can bring everybody together to ensure the future success of the project. When we're planning a building and doing a mechanical design, it's primarily an exercise in understanding where the loads come from. Most of that means we need to understand the building envelope. These are my mechanical designs, and I start from modeling the entire building, all of the walls, floors, and roof assemblies, as well as windows and doors, and ventilation loads, and any other internal loads that are going to occur. All of those factors come together to give me a total BTU rating for my maximum load, and that's what my system has to be able to service. Our code requirement is that we do a CSA F280 12 room-by-room heat load calculation. That tells us exactly how much heating and cooling we need to deliver to each room of the house and dictates the rest of the duct design. In addition to the building envelope elements that make up the shell of our building, where we lose energy or gain energy from the exterior environment, we have several other factors that go into the mechanical design. One of the primary ones is our infiltration level. That is our airtightness score, and if we're targeting for certain levels of step code, we know exactly what value to use for that. On a step 4 home, we're using 1.5 ACH, and that's going to dramatically reduce our infiltration load, allowing us, if we're on the margins, to size down our mechanical system. We also have our HRV and ERV, which we'll get into the efficiencies of those later, but those dramatically influence the amount of heating and cooling that we need to put into the air as well. When adding our inputs for a mechanical design, we have to think about occupant behavior. I'm going to put a lot more cooling load into a kitchen than I am into a living room or a bedroom, because we're going to be cooking in there. People are going to be congregating in there. So that's an occupant behavior we have to account for, or the kitchen is not going to be able to be maintained as comfortable. Our design conditions that we put into a building and into a mechanical design determine the capacity of the system. That's a big factor in what we're going to be getting out of our design. The design conditions for interior environment that are set out in CSA F280 are set there not for occupant comfort, but for safety. If your occupants are going to require that their house is able to be kept at 20 degrees Celsius, you have to adjust your interior design condition. Also, we have to be thinking about the way that the building is constructed and the area that it's constructed in. There are a lot of different things that will affect our mechanical design, and we want to make sure that our mechanical systems can overcome the conditions that they're presented with. With every decision that we make within the design, we have to be considering cost. The cost of construction has gone up dramatically in the last 10 years, and we have to be mindful of what we're doing with our clients' money and involving them in the process. Each decision that we make is going to come with an upfront cost for the materials that we purchase in order to make the design happen, and then ongoing costs in terms of maintenance and energy consumed through the life cycle of that equipment, and then the actual lifespan of the equipment is what we have to consider too, and replacement value. If we're thinking about all of those things while we're doing the design, we can optimize for lower costs over the whole lifetime of our project for our client. So once we've taken care of our inputs and we know what our loads are going to be and how we need to design our duct system in order to service that, these are the things that we'll get out of this. On here, we have a supply branch table that tells us what size of ducts we're going to be servicing for which room in order to meet which of the design conditions, whether the heating or cooling load is the dominant. From there, we'll plan our duct runs and make sure that they're going to work with the structure of the building. We have to ensure that where we locate our supply and return ductwork, and as well as the vertical stacks that go through the different floors of the house, that is going to work architecturally for the design of the building. With modern airtight homes, we're testing to make sure that they are not leaky. And you will often hear older builders say that a home needs to breathe. Well, I agree that a home needs to breathe, but when I breathe, I don't do it through my skin, the building envelope. I do it through my lungs. So the BC Building Code requires that we provide fresh ventilated air at a certain level based on the square footage and number of bedrooms of a house. We're going to do that through the lungs of the house, which is going to be the HRV. If we look at the HRV that we have installed in this home here, we have 4 pipes coming out of the top of it. 2 of them go to the outside, 1 for bringing in fresh air and 1 for expelling stale air. The other pipe networks go to the different areas of the house. We're drawing exhaust air from dedicated portions of the house to remove that air from the home, and then we're supplying via this pipe up here fresh, filtered outside air that's had the heat recovered from the outgoing air to our return air plenum for our furnace. The furnace then takes that air and distributes it throughout the house. We're required to provide 10 CFM to every bedroom and 20 CFM to a primary bedroom, as well as providing fresh air to all livable areas or levels of the home. That's a code requirement, we can't get away from it. We have to do this in the most efficient way possible, and that includes selecting high quality, efficient equipment. One of the things that builders need to be able to read and look at for this type of equipment is the efficiency label, which is located either under or on the side of the unit. The average home in Kelowna that's built, a custom home, is over 3,000 square feet and generally has 4+ bedrooms. That means we're going to have to supply 90 CFM or more of continuous ventilated outdoor air to maintain the indoor air quality. That's a code requirement, so we have to make sure that we're understanding the efficiency with which we're doing that. The numbers that you're seeing on these labels are sensible recovery effectiveness. So what does that mean? That is the amount of energy that the HRV is able to take out of the outgoing air that it's exhausting to the exterior and put into the incoming air by exchanging it across a core. So on this HRV, you can see that we have a core inside here. This core is made of a bunch of little tubes that don't intersect but pass by each other. The incoming air from the outside gets passed through the core, and as it passes along adjacent to the tubes coming from the inside air, we exchange the energy between them. So the incoming air is heated or cooled by the outgoing air, allowing us to reduce the amount of energy that it takes to condition that air once it's inside the building envelope. So this is a different piece of equipment. This is an ERV. That's slightly different than an HRV in that it's an energy recovery ventilator, meaning that it will exchange not just the heat, but the moisture from the air, which is an additional load. On here, we have a sensible recovery efficiency of 89% at 0 degrees Celsius, which is meaning that only 11% of the energy in the air is lost as we ventilate it out. Now, we get that done based on this very large core in here and the long pathways that the air has to travel through in order to exchange from inside to outside. That allows the air more time to pass through the core and exchange its energy with the incoming air. One other important feature of an HRV or ERV is to have active dampers like seen here and here and here. Those dampers allow the unit to adjust and balance itself as well as to close down when not in use, so that we don't end up with an open pipe to the outside, reducing our energy efficiency. One other feature of ERVs when compared to HRVs is that they do exchange the moisture from the air while they pass the air through the core. So that means that we don't have to have a condensate drain coming out the bottom of this unit. We can have just a free and clear installation with no tie-ins to the plumbing system because the moisture doesn't condense within the core. It's actually passed through the core without contaminating the air. Our second main piece of mechanical equipment is our domestic hot water system. Most of them will be something like this, a storage tank that's powered either by electricity or gas. You can also have instantaneous boilers that are powered by electricity or also by gas. With a storage tank like this, from a cost of installation and a cost of replacement perspective, you're going to have a lot lower cost of ownership over the long term. Now, we have different types of storage tanks, and some of them have an integrated heat pump that allows us to grab heat out of the air and put it into the water. Now, in the summertime, that's going to give you a nice cooling bonus in your home because you're going to be taking heat out of the air that you would otherwise have to pay to air condition out with your heat pump or your air conditioner, and you're putting it into the water so that you can just wash it down the drain when you shower. Our primary piece of equipment in most homes is going to be a piece of equipment that looks something like this. At its core, it's a big fan that blows air around the building. We have different methods of adding heat or subtracting heat from that air in order to keep the occupants comfortable. This here is a gas furnace. It's pulling air through this return plenum and through this filter and pushing it out the top through this piece of equipment, which is our heat pump coil, which is going to put heat or subtract heat from the air as it passes through, and then it gets delivered through the rest of the house. On top of the air handler, we have our heat pump coil. Now this is a coil that leads from the outdoor condenser with these refrigerant pipes and exchanges energy with the outdoor environment as the air blows across it. This is a very important piece of equipment because it provides all of our cooling for this home and a large part of our heating. When we look at these pieces of equipment, we should be thinking about the energy that they consume. They're going to consume energy from electricity, as well as in this case, we're going to be consuming natural gas. Most natural gas condensing furnaces, and you can tell they're condensing because of the ventilation pipes that are coming out of the top here, as well as the condensate drain. All new homes that have a gas furnace will have a condensing furnace. Now, those are all going to be very much the same efficiency for their use of gas, but the blower inside is actually a very important piece of equipment. The motor that powers the air around the house can be done in two different ways in modern equipment. We can have an ECM motor with different speed settings. You can have low, medium, high, or even sometimes 5 speed settings on an ECM motor, or you can have a continuously variable motor. Those are going to consume power in very different ways based on how the ducted system is designed and where we're putting the CFM. Any air handler powering a modern house is going to have a constant draw. It's going to be running that fan 24 hours a day, 7 days a week, if we don't have a dedicated ducted system for our ventilation. Most homes are going to use the HRV or the ERV, put it to the return air plenum for the furnace, and then use this to circulate it around the house. That fan motor is a constant draw 24 hours a day, like I said. Some settings on these furnaces are going to cause them to consume 125 watts. Some settings, based on the duct design, are going to cause them to consume 75 watts. That's a pretty broad range, and we could be reducing our energy draw by 50 watts 24 hours a day if we make the correct decisions when we design our ducts and when we install our ducted system. One of the final things we're going to be doing when we're getting a house ready for occupants to move in is commissioning and balancing the mechanical and ventilation systems. Now, we're going to do that by use of a flow hood. This isn't as common in residential as it is in commercial, but it's a very good tool that you can use to set yourself up for success and make sure that your clients are going to be happy. We've already done a duct design. We already have a heat load calculation. We know how much air we have to put into each area, so then we commission the system. And this is where it becomes very important that we've engaged with our design team and we've talked about vent covers at the very beginning of the process. Most systems are designed to use a vent cover like this, or a vent cover like this that has a certain amount of free grill area. If we end up with a client who all of a sudden makes a decision to use this type of flooring insert vent cover, that's going to introduce a whole lot of restriction that we weren't planning for. And you can see that with that in, compared to the baseline of what I just showed, we only get a certain amount of airflow through there. It's a restricted airflow that we have to be planning for in the very beginning. So we want to make sure that we've had those conversations with our clients. 34 CFM coming out of there right now. Whereas if we were planning on our system delivering 40 plus CFM of air in order to keep everybody comfortable, then we're going to have to change some system settings and use a lot more energy. You can see here that if I was commissioning this system using these vents, I'd be getting 44 CFM of air out of there. And that's a big difference. That's a 30% increase in airflow coming out of this vent compared to another with the exact same furnace settings. So now the home is complete and we have our clients moving in. This is the one part of the mechanical system that they are going to interact with the most. It needs to be set up well and have them educated on how to use it so that they can remain comfortable within their home.